Hey everyone, today we're going to talk about section 3.5. This is on real zeros of polynomials. So in this section we're going to learn how we can find good candidates to test using synthetic division. The techniques that we're going to demonstrate in this section are maybe somewhat antiquated because we have easily accessible graphing technology like Desmos. But these techniques can sometimes be useful in helping us find the bounds of our zeros or possibilities for rational zeros. First up, we're going to talk about this thing called Cauchy's bound. Cauchy's bound gives us an interval on which all of the real zeros of a polynomial can be found. This tells us, given some polynomial, let m be the largest of the coefficients in absolute value. Then all the real zeros of f of x lie in the interval negative m over absolute value of a sub n, which is the leading coefficient, minus 1, comma, m divided by absolute value of a sub n, which is the leading coefficient once again, plus 1. And really what this is telling us to do is to find the largest of the coefficients and take the absolute value of it, right? Find the largest of the coefficients in terms of magnitude and take the absolute value of that thing. We're going to look at an example right now. Let f of x equal 2x to the fourth plus 4x cubed minus x squared minus 6x minus 3. Determine an interval which contains all the real zeros of f. So our Cauchy's bound is, let's just recall from the last page, negative m over absolute value of a sub n minus 1, m over absolute value of a sub n plus 1. Here, m is going to be the largest of these coefficients in terms of absolute value. The largest number here I see here is negative 6. So m is going to be the absolute value of negative 6, which is positive 6. A sub n is going to be the leading coefficient. The leading coefficient here is 2. Notice then that this means that the absolute value of a sub n is also just 2. So this Cauchy's bound, this interval in which all of my real zeros must exist, is the closed interval. Notice that these are square brackets. From negative, m is 6 over absolute value of a sub n is 2, minus 1, 6 over 2 plus 1. And this simplifies to, let's see, negative 3 minus 1, comma, 3 plus 1. And this gives me the interval negative 4 to positive 4. Both of these endpoints being included because I have square brackets for both of them. Knowing this kind of bound can be helpful when we're using something like a graphing calculator, because we can set the bounds of our display in that graphing calculator or in Desmos even. This lets us narrow down the area that we're looking at on the graph. Let's look at another example. Determine an interval which contains all the real zeros of 3x cubed minus 12x squared plus 6x minus 8. Well, here, m is going to be the absolute value of negative 12. Negative 12 is the largest number I see here. And this is just positive 12. A sub n, this is the leading coefficient. The leading coefficient here is 3. And the absolute value of 3 is just 3. Right, the absolute value of a sub n, right? So putting everything into Cauchy's bound, remember Cauchy's bound is negative m over absolute value of a sub n minus 1, m over absolute value of a sub n plus 1. this is going to be negative 12 over 3 minus 1, 12 over 3 plus 1, and this is negative 4 minus 1, comma, 4 plus 1, and this is the interval from negative 5 to positive 5, square brackets on both of these endpoints. All of the real zeros of this polynomial must lie in the interval from negative 5 to positive 5, including those endpoints, meaning the zeros could be at negative 5 or at positive 5. And this is Cauchy's bound. So, looking at the next part of this section, we have this thing called the rational roots theorem. The rational roots theorem provides us with a list of possible integer and rational zeros. So integers are rational numbers by definition, right? Rational numbers are just numbers that can be expressed as a ratio. And integers themselves can be expressed as a ratio. So the rational roots theorem tells us if we're given a polynomial with integer coefficients, then if r is a rational zero of f, then r is of the form r equals plus or minus p divided by q, where p is a factor of the constant term, the thing that we're adding or subtracting at the end, and q is a factor of the leading coefficient. So r is of the form of some factor plus or minus a factor of the constant divided by a factor of the leading coefficient. And if we do every possible permutation of this, then we'll have a list of all of the possible rational zeros of a polynomial. Let's look at an example. This is actually the same polynomial that we looked at before. The first one, at least, that we looked at with Cauchy's bound. Let f of x equal 2x to the fourth plus 4x cubed minus x squared minus 6x minus 3. Use the rational roots theorem to list all the possible rational zeros of f of x. So I need all of the possible factors of a naught, which is my constant at the end, right? This is negative 3. And I need all of the possible factors of what we can call a sub 4, which is 2. This is my leading coefficient. I need all possible factors of this constant and all possible factors of my leading coefficient. So p is all possible factors of the constant here. The only factors of 3 are going to be 1 and 3. The only factors of 2, these are going to be my q's, are going to be 1 and 2. This means that these possible rational roots are going to be plus or minus 1 over 1, plus or minus 3 over 1, plus or minus 1, or let's see, 1 over 2, and plus or minus 3 over 2. This is all possibilities of p over q. This is all of my possible rational roots. And of course, notice that this is that 1 divided by 1 is 1, and 3 divided by 1 is 3. So we can rewrite the list as this. These are all of the possible rational roots of this polynomial. If I know all of the possible rational roots, then I can perform some synthetic division to help narrow down the possible zeros of this polynomial. Using Cauchy's bound, graphing and this list of rational roots that I found. So let's look at another example here. Let's find the horizontal intercepts of that same polynomial. This is the same polynomial that we've seen already. In order to do this, first we really want to graph this thing. You can do this in a TI-83 or TI-84 or a Casio equivalent. So this is what the graph of this function looks like. Remember that all real zeros lie in the interval. We actually found Cauchy's bound for this previously. All of my real zeros for this exact polynomial lie between -4 and +4, which is why I've restricted the window here. And by possible rational roots, which we just found, my possible rational roots were plus or minus 1, plus or minus 3, plus or minus 1/2, and plus or minus 3/2. Now we can look at the graph here to determine what a possible rational root is for this polynomial. It looks like there might be a root at x equals -1. I can zoom in a little bit so we can maybe see that a bit easier. It looks like at x equals -1 here that it might touch the x-axis, right? And maybe it bounces off or maybe it crosses through. It's kind of hard to see. This is intentional because if you use something like a TI-83, it's going to be difficult to see this thing unless you zoom in really, really closely. So we're going to try some synthetic division with x equals -1. Let's try this as a guess. Let's try x equals -1 as a guess. And this will help us find some additional zeros. And I suspect that if x equals -1 is, in fact, a root here, that it's occurring more than once, right? It looks like this either bounces off the x-axis and goes down just a little bit before crossing back through it, or it crosses through the x-axis here. So I'd say x equals -1, if it is a root, has either multiplicity 2 or 3. So we're going to set up our synthetic division. If x is equal to -1, then -1 goes in the box. I write all of the coefficients of this polynomial: 2, 4, -1, -6, -3. The 2 comes straight down. 2 times -1 is -2. 4 plus -2 is 2. 2 times -1 is -2. -1 plus -2 is -3. Times -1 is +3. -6 plus 3 is -3. -3 times -1 is +3. And -3 plus 3 is 0. So x equals -1 is in fact a root of this polynomial. And once again, I believe that this 0 has at least multiplicity 2. It has either multiplicity 2 or 3. So let's attempt polynomial division one more time with x equals -1. So -1 goes in the box. I'm going to bring down these new coefficients that I found here. And let's see, the 2 comes straight down. 2 times -1 is -2. 2 plus -2 is 0. 0 times -1 is 0. -3 plus 0 is -3. And -3 times -1 is 3. And -3 plus 3 is 0. So once again, I got a remainder of 0. So x equals -1 is a root that occurs at least twice here. I think, though, that this root is only going to occur twice, because what we have left here is 2x squared minus 3. I can actually find the last two roots now easily. So I know that x equals negative 1 with multiplicity 2 is, in fact, a root, right? X equals negative 1 is a root with multiplicity 2. I can take what I have left, I can take this quotient from my synthetic division and set it equal to 0 and find these remaining two roots. If I add 3 to both sides, I get 2x squared equals 3. I divide both sides by 2, I get x squared equals 3 halves. And I take the square root of both sides, and I get x equals plus or minus the square root of 3 halves, which can also be rewritten as plus or minus the square root of 6 over 2. So these are my other two roots. I have x equals negative 1. This has multiplicity 2. X is negative square root of 6 over 2. And x is positive square root of 6 over 2. And these are all of the horizontal intercepts of this polynomial, or all of the real zeros. What is that? It asks for horizontal intercepts, which these are the same thing. Let's look at another one. Find the real zeros of 4x cubed minus 10x squared minus 2x plus 2. I suppose that first we should find Cauchy's bound, right? To find the interval that we're really restricting ourselves to. Cauchy's bound here would be, let's see, 10. The absolute value of negative 10 is 10. Or let's see, I need a negative sign here. Over absolute value of 4 is 4 minus 1, comma, 10 over 4 plus 1. And I'm going to get negative 3.5 to 3.5. So all of my real zeros must occur in this interval. Now I've graphed this for us here. Let's see. Let's look at our rational roots theorem so we can actually do something with this graph. I need all factors of 2. So p is 1 and 2. I need all factors of 4. This is 1, 2, and 4. So this means r is plus or minus 1 over 1 plus or minus 2 over 1 plus or minus 1 over 2 plus or minus 2 over 2 plus or minus 1 over 4 and plus or minus 2 over 4. This is all this is plus or minus all possible p's over all possible q's. And I think this actually simplifies a little bit because some of these are the same, right? This first one is r equals plus or minus 1 plus or minus 2 plus or minus 1/2. 2 over 2 is just 1 plus or minus 1/4. And 2 over 4 is just 1/2 again. So really I just have these 8 possibilities, right? Really these are 8 possibilities because I have plus and minus. Let's see. It looks here like plus or minus 1/2, judging by the graph here. It looks like plus or minus 1/2 are the most likely to actually be roots. Plus or minus 1 wouldn't make any sense, right? Plus or minus 1 are here and here. I definitely don't have roots there. Plus or minus 2, well, I definitely don't have roots there or there. right? So I can actually cross, oh, I didn't mean to do that. Let me undo. I can actually cross those out. Plus or minus 1/4, I would expect to be really close. I would expect to be like here and here or so. So really, those don't make any sense. Plus or minus 1/2. Those are really going to be the only possible rational roots here, right? And notice that the plus 1/2 looks like a... to me, it looks like plus 1/2 is probably not going to be it, but we'll test it anyway. Let's go ahead and say x equals 1/2. 1/2 goes in the box. My polynomial is 4x cubed minus 10x squared minus 2x plus 2. So these coefficients are 4, negative 10, negative 2, and 2. The 4 comes straight down. 4 times 1/2 is 2. Negative 10 plus 2 is negative 8 times 1/2 is negative 4. Negative 2 plus negative 4 is negative 6 times 1/2 is negative 3. 2 plus negative 3 is negative 1. I have a remainder of negative 1 here. And because I have a remainder, that means that x equals 1/2 is not a 0. Let's try instead x equals negative 1/2. Then negative 1/2 goes in the box. These coefficients are the same. The 4 comes straight down. 4 times negative 1/2 is negative 2. Negative 10 plus negative 2 is negative 12 times negative 1/2 is 6. Negative 2 plus 6 is 4 times negative 1/2 is negative 2. I get a remainder of 0. This means that x equals negative 1/2 is a 0. So this means that 4x cubed minus 10x squared minus 2x plus 2 is x plus 1/2. This gives me x equals negative 1/2 times, let's see, 4x squared minus 12x plus 4. Now, if I want to find these remaining two intercepts, I can use quadratic equation with this quadratic that I have here. Let's see. And really, I can actually factor out a 4, and it can make my math a little bit easier, right? Because if I factor out a 4 and set this equal to 0, this is the same thing as if I just have this thing equal to 0, right? Just by factoring out this 4. You can leave the 4 in, and you'll get actually the same answers. Get the same exact answers regardless. But this will make our arithmetic a little bit simpler, because now a is 1, b is negative 3, and c is 1. So x is opposite of b plus or minus square root. Maybe I'll put opposite of b like this. Negative 3. Plus or minus square root b squared minus 4ac all over 2a. This is 3 plus or minus square root, let's see, 9 minus 4, which is 5, all over 2. And if I plug this into a calculator, so you would want to enter these separately as exact answers into something like MyOpenMath. You would want to list this as x equals 3 plus root 5 over 2, 3 minus root 5 over 2, if you were entering this in MyOpenMath, because an exact answer is preferred. If we wanted to know what this was as a decimal, approximately, this is about 2.618, 0.382. And we'll look at one more. Find all the real zeros of this thing. Let's see. Cauchy's bound here is going to be negative 6 over 3 minus 1, 6 over 3 plus 1. This is going to be negative 3, positive 3. For my rational roots theorem, all the factors of 2 are 1 and 2. All the factors of 3 are 1 and 3. So r is plus or minus 1 over 1, plus or minus 2 over 1, plus or minus 1 over 3, plus or minus 2 over 3. If I look at my graph to find what some reasonable roots are here, let's see. Looks like plus or minus 1. Looks like that's not going to be it. Let's see. Plus or minus 2. It also looks like that's not going to be it. Plus or minus 2/3. 2/3 would be like here and here-ish. So it looks like that's not going to be it. And it looks like minus 1/3 also wouldn't be it, because minus 1/3 would be here-ish. So the only possible rational root that I can see here would be x equals positive 1/3, because it looks like x equals negative 1/3 won't be it. So x equals positive 1/3 could possibly be it. Let's see. We have 3x cubed, so 1/3 goes in the box. Oh, sorry. 1/3 goes in the box. My coefficients here are 3, negative 1, negative 6, and 2. The 3 comes straight down. 3 times 1/3 is 1. Negative 1 plus 1 is 0. 0 times 1/3 is 0. Negative 6 plus 0 is negative 6. Times 1/3 is negative 2. Negative 2 plus 2 is 0. So it looks like x equals 1/3 is a 0. What I have left here is 3x squared minus 6. If I set this equal to 0, let's see. I can factor 3 out of everything. I have 3 times x squared minus 2 equals 0. Divide both sides by 3. I get x squared minus 2 equals 0. Add 2 to both sides. I get x squared is 2. And when I take the square root of both sides, I get x is plus or minus the square root of 2. So all of my real zeros are x is positive 1/3. X is positive square root of 2, and x is negative square root of 2. And that seems to line up with this, right? These are between 1 and 2, like the square root of 2 would be. And that's going to be it for 3 to 5, a bit of a short section.